Welcome to the deep dive. Today, we're really getting into the heart of industrial operations. It's a world where, well, everything hinges on precision, doesn't it? And there's this absolute need to avoid unplanned failure at all costs.
Absolutely. It's baked into the DNA of anyone running these kinds of facilities. We're not just talking about machines here.
No, it's bigger than that. It's
Yeah.
really about, stewardship of assets, keeping things running, and protecting that bottom line.
That's the critical frame, yeah.
Yeah.
For plant managers, for engineers on the floor, reliability isn't just a spec on a sheet. It's the ultimate measure of whether you're in control.
And that control slips.
Well, that's when the costs just explode. It's not a gentle slope. It's a cliff edge financially.
Okay, let's put some numbers on that right away because I think that really sets the stage. We looked at the data, and for a typical industrial business, unplanned downtime, it's not small change.
Not at all.
The average figure is around $103,000 per hour.
Per hour. And honestly, that often feels conservative depending on the industry.
Right, because if you look at, say, a big automotive plant or maybe a complex chemical facility.
Oh, easily. Those numbers can shoot past $2 million an hour. It's almost hard to fathom.
And over a year.
Yeah.
What does that look like? We saw estimates around, $129 million for an average large plant?
Yeah.
Just lost, gone.
$129 million annually, just because something stopped working when it wasn't supposed to. That's the price tag on instability. It's staggering.
It really is. And that kind of number, well, it forces you to rethink everything, doesn't it? About how we approach reliability in the first place.
Exactly.
So that's our mission today. We're going to take apart, really examine the Graco SoloTech peristaltic hose pump. Because it's engineered specifically, it seems, to attack those very failure points that lead to these massive costs, to eliminate them.
And we need to look at it from two angles, really. First, yes, the pump itself, the hardware, the engineering design, which is quite distinct. But second, and this is just as vital as the human element, the expertise needed to make sure that technical potential actually turns into real-world uptime.
Ah, right. You're talking about the master specifier role, James Riggins.
Precisely. James Riggins. He embodies this idea of let's call it a life cycle guarantee posture. It's about ensuring the right pump goes into the right application correctly from the very beginning.
Got it. Hardware and expertise working together. Okay. So to really get why the SoloTech might be necessary, we probably need to start with the problem, right? What's wrong with the pumps many plants are using now?
Well, we have to talk about this concept of a false economy. It sounds a bit harsh, but
Johan?
Many conventional pumps, especially for metering or handling slurries, they're based on designs that are frankly quite old. And these designs have inherent compromises built right in.
Compromises how?
They rely on component-specific parts that everyone knows are going to wear out, leak, or just fail relatively quickly. In a way, you could almost say they have a predictable obsolescence factored in.
Engineered to fail. That sounds quite pointed. Is it really a flaw or just, the reality of tough industrial environments? Where do these pumps actually break down?
It's often in the way they try to keep the fluid contained while still driving it.
Yep.
The weak points, almost universally in traditional designs like centrifugal, piston, or diaphragm pumps, are things like the valves, seals, or glands.
Okay, those specific components.
Yes. They're essential in those designs to maintain pressure, stop backflow, contain the fluid, but they're also the parts constantly under stress.
And when you throw tough stuff at them, like abrasive slurries in mining, or maybe corrosive chemicals in wastewater treatment.
That's exactly where they become the failure hotspots. Think about slurries, sharp particles just grinding away at mechanical seals or valve seats. Leak paths form quickly.
Right.
Or in chemical dosing, you get chemical attack on the seals. They might swell up, get hard and brittle, or just fail catastrophically. Even with viscous fluids, things like check valves can get gummed up, they crystallize, and suddenly your dosing accuracy is gone. These parts just demand constant attention.
Constant cyclical maintenance. And that's where the real cost starts to add up, isn't it? It's not just the part, it's the labor, the downtime.
It's a huge operational burden. The numbers are pretty consistent across industries. Maintenance, repair, keeping things running. It often eats up between 35 and 50% of a plant's entire annual operating budget.
35 to 50%. That's incredible. Half the budget potentially just fixing things.
Think about that. Almost half your funds aren't going to making things better or faster or more efficient. They're going to just stopping things from breaking down, cleaning up spills, replacing parts you know are going to fail again.
It's a treadmill of repairs.
It is. And it's a cycle that forward-thinking engineers and managers are desperate to break. You can't sustain that kind of cost inertia. The whole mindset has to shift.
From just managing failure.
To actively engineering reliability from the ground up. Proactive, continuous uptime. That has to be the goal.
Okay, so if the root problem lies in those predictable failures, the valves, the seals, then the SoloTech has to tackle that head on. Let's pivot now to the solution. How does this pump actually engineer uptime?
The absolute core difference, the foundation of its design, is its sealless architecture.
Sealless. Okay.
It sounds simple, but it's profound. If the main failure points are seals and valves, well, you just design them out completely.
How does that work mechanically? How do you pump something, especially something corrosive or abrasive, without any seals to contain it?
It uses the peristaltic principle. Think of how muscles contract to move things along, like in your digestive system, but obviously engineered for heavy industry.
Okay.
The fluid itself is entirely contained within a single, robust, specially engineered hose. That's it. The pumping action comes from an external roller that gently compresses the hose against a fixed track or casing.
Ah, I see. So the fluid literally never touches any moving mechanical parts outside of that hose.
Precisely. Because of that, the need for traditional mechanical seals or packing glands or even check valves, it just disappears. They aren't necessary for the pump to function.
That's a fundamental shift, not just improving a component, but eliminating the vulnerability altogether.
Exactly. And that inherently makes the pump mechanically simpler and, crucially, much less expensive to maintain over its life.
Okay, but what about the hose itself? That's now the only part really in contact with the fluid and taking the mechanical stress, right? How do you make sure that lasts?
That's the next critical piece of the engineering. And this is where Graco went beyond just a standard peristaltic design. They developed what they call single roller compression.
Single roller compression. Okay, break that down. What makes that different or better?
Well, most conventional peristaltic pumps use 2, sometimes even 3, rollers, or what they call shoes, that press down on the hose multiple times with each rotation of the pump track.
Okay, multiple squeeze points per cycle.
Right. And that constant multiple compression generates quite a bit of friction and heat, especially if you're running at higher speeds or pumping something thick and viscous.
And heat is the enemy of rubber and elastomer hoses, right? It degrades them.
Exactly. Heat and the repeated stress cycles, that cyclical fatigue, that's what primarily wears out the hose material in those traditional designs.
So how does the single roller change that?
The SoloTech uses just one large diameter roller. This roller compresses the hose only once during a full 360-degree rotation of the drive.
Ah, okay. Only one compression event per revolution.
Yes. And this means the hose material gets the maximum possible time to relax and recover between each compression stroke.
I see. That longer relaxation period lets the elastomer dissipate any built-up heat and sort of regain its shape, its mechanical memory, reduces the stress.
Precisely. It minimizes that cumulative fatigue effect. The design is also optimized, the way the roller interacts with the hose over a specific arc, to reduce shear stress at the contact point.
So less heat, less friction, less fatigue overall, even though it's one point of contact.
Correct. And the net result, the measurable benefit of this single roller approach, it extends the operational life of that hose by 30 to 60% compared to the older multi-shoe designs running under the same conditions.
30 to 60% longer life for the main wear part? That's a huge difference in maintenance schedules.
It translates directly into fewer planned shutdowns, less labor time changing hoses, lower costs for replacement parts. It's engineered longevity, plain and simple.
And that reliability mindset, does it carry over into how the pump handles problems? Like what happens if a line gets blocked?
That's another key operational advantage. The pump is fully reversible, instantly reversible.
Why is that so important on the plant floor? Usually if a line plugs up, it's tools out, lockout, tag out, right? Takes time.
Exactly. Think about a line getting blocked, maybe some crystallized chemical or a really thick slug of slurry. In a traditional system, you're looking at potentially hours of downtime.
Yeah, you have to shut down, isolate, probably send a maintenance crew.
Right. They have to follow all the safety procedures, get pipe wrenches, physically break open a flanger connection, manually clear the blockage, and often deal with spills and hazardous material exposure in the process.
A major headache, and potentially dangerous too.
Definitely. With the SoloTech, the operator can often just hit a switch and reverse the pump's direction.
And that does what?
That reversal creates a powerful suction or pushing action back the other way. Very often, it can immediately dislodge the blockage, pulling the material back towards the source tank, or just clearing the obstruction in the line.
Without ever needing to open up the piping?
Without cracking a single flange or taking anything apart, That ability to potentially resolve a blockage in minutes just by reversing the motor instead of hours of manual labor, that's a massive win for uptime and safety.
Yeah, I could see that. Huge difference. Okay, so it's reliable, it recovers quickly. What about precision, especially for things like chemical dosing where accuracy matters a lot? How does it compare there?
It excels there too, largely due to its high volumetric efficiency. It delivers a consistent, predictable amount of fluid with each rotation.
Meaning?
We'll take a model like the I-26, for example.
Mm.
It can deliver up to about 0.11 gallons per single revolution. That's quite a bit.
Okay.
This means two things. One, for a given target flow rate, the pump can often run at a lower RPM, which is gentler on the hose, and extends its life even further.
Lower speed, less wear. Makes sense.
But maybe more importantly, especially for dosing, this high efficiency per revolution allows for much smoother and more accurate turn down.
Turn down control. What does that mean in practice for, say, a process engineer?
It means getting consistent, linear flow control, even when you need very low flow rates. Many traditional pumps, like diaphragm pumps, can become quite pulsy or erratic when you try to run them near their minimum output.
Right, you get surges instead of a smooth stream.
Exactly. That pulsation leads to inaccurate dosing, sometimes too much chemical, sometimes too little, which means wasted material, potential quality issues in the final product, or ineffective treatment. The SoloTech, being a positive displacement pump with that smooth single roller action, provides a very linear, predictable flow across its operating range. This allows for much tighter control over dosing, minimizing waste and variability.
Okay, so that inherent stability, that precision, that's really the bridge connecting the engineering benefits to the actual dollars and cents, the ROI. Let's make that link really clear now. How does all this translate to the plant's budget?
Directly into reduced operational expenditure OPEX. It's pretty straightforward. When you eliminate the parts that need frequent attention, like mechanical seals and check valves.
You eliminate the labor cost associated with fixing them.
Exactly. You cut out the routine maintenance hours spent replacing seals, adjusting packing glands, taking apart valves to clean them. Plus, you reduce the costs and potential fines associated with cleaning up spills from leaks.
So what kind of numbers are we talking about annually per pump?
Looking at the data, conservative estimates put the annual OPEX reduction somewhere in the range of $1,200 to $2,400 per pump.
Just from reduced maintenance labor and spill cleanup?
Just from that alone, yes. And if you have a facility with, say, 20 or 30 of these pumps in critical spots, well, you can see how those savings add up very quickly. It easily gets into six figures annually across a plant.
That's substantial. And this isn't just theoretical, right? There are real-world examples backing this up, especially on the longevity front.
Oh, absolutely. The water treatment industry provides some really compelling case studies. It's notoriously tough on pumps due to corrosive chemicals like polymers and hypochlorite.
Okay, like what?
There's a well-documented case at the Oak Ridge, Tennessee water treatment plant. They ran a peristaltic pump for polymer dosing.
Which is sticky, viscous stuff, right?
Very. And potentially abrasive, depending on the mix.
Yeah.
They achieved 3 full years of continuous operation with that pump.
3 years. And the key metric?
0 reported leaks and 0 unplanned maintenance downtime related to the pump itself in that entire 3-year period.
Wow. 3 years, leak-free on polymer. With traditional tech, you'd expect issues much, much sooner, wouldn't you?
Absolutely. That level of reliability and that kind of service is, frankly, almost unheard of with pumps relying on seals and valves.
Yeah.
It's powerful proof of the sealless, single-roller concept working in the real world.
Okay. Any other examples, maybe on the cost side?
Yeah, similar findings came from the city of Lompoc in California, another water treatment plant. They also reported significantly lower overall operating costs after switching to this type of peristaltic technology for some demanding applications. That includes both power consumption and maintenance expenses.
Power consumption. That's interesting. Let's touch on that. Pumping thick stuff, slurries, viscous fluids, that takes energy. How do these compare?
They are remarkably energy efficient, especially in high-demand duties like handling thick underflow from clarifiers, which you see a lot in mining and wastewater.
Okay.
Compared to traditional centrifugal pumps doing the same heavy lifting, peristaltics typically use only about 50% of the electricity.
60%, so a 40% saving on power.
Roughly, yes. And they often use significantly less water, too, maybe only 25% of the flush water, sometimes needed for centrifugal seals in slurry service.
That's a big difference in resource use if you translate that energy saving into dollars for, say, a municipal plant budget.
We have data from one specific municipal plant showing an annual energy saving of $1,775 per pump, just from the lower electricity draw.
$1,775 a year per pump, just on energy.
Correct. And when they calculated the payback based on that energy saving alone, it was less than 2.5 years.
Wow, so the pump pays for itself pretty quickly just on electricity, even before you factor in the massive savings from avoided maintenance and downtime.
Exactly. It shifts the perspective. It's not just a capital expense. It's an immediate OpEx reduction strategy with a very fast, quantifiable return.
Okay, the technical side is solid, the ROI seems undeniable, and that combination of reliability and cost-effectiveness must make this pump useful in a lot of different areas, right? It's not just for one niche.
Its versatility is a huge strength, yeah. Because it handles difficult fluids so well without wearing out seals or contaminating the product, it solves chronic problems across many different industrial sectors. We generally see it dominating in about 4 key areas.
All right, let's hear them.
First, abrasive slurries and solids transfer. This is classic mining, cement production, handling thick wastewater sludge. Places where hard particles just chew up traditional pumps. The SoloTech keeps the slurry inside the hose, away from moving parts. Big advantage.
Okay, abrasives. What's next?
Second, chemical dosing and corrosive fluids. Super critical in water treatment, obviously, for things like polymer, sodium hypochlorite, acids, caustics. Also important in oil and gas for chemical injection. The sealless design is huge here. No leaks, no fugitive emissions, and it doesn't get clogged by chemicals crystallizing like check valves do.
Right, safety and consistency.
Oh, yeah.
Third.
Third area is viscous and shear-sensitive materials. Think food processing sauces, fillings, cosmetics, creams, lotions. Also specialty polymers or adhesives where you can't damage the fluid structure by pumping it too roughly. The gentle rolling action of the peristaltic is ideal for preserving product integrity.
Protects the fluid itself.
Yep.
Okay, and the last one.
And fourth, coatings, pigments, and adhesives. Industries like automotive manufacturing, painting lines, electronics assembly. Here, inconsistent flow or clogging from sticky materials can ruin product quality. The SoloTech gives that tight volumetric control and just isn't bothered by the sticky nature of these fluids. Ensures a consistent application.
Okay, so mining, chemicals, food pharma, manufacturing, it really does cover a lot of ground. So we've got the pump itself, mechanically robust, leak-free, efficient, versatile. That's the SoloTech hardware. But like we said at the start, that's only half the story, right? The best tool in the world doesn't help if you use it wrong. Now we need to talk about that human element, the James factor.
Yes, this is absolutely crucial. You can have the most brilliantly engineered, reliable pump design imaginable. But if it gets misapplied...
What do you mean misapplied?
If someone specifies the wrong hose material for the chemical being pumped, or they choose the wrong size motor, or they try to run it way too fast outside its optimal RPM range for that specific fluid,
then all that engineered longevity, the single roller benefit, it just evaporates.
instantly negated.
Yeah.
You'll get premature failure, leaks, all the problems you thought you were solving simply because the application wasn't matched correctly to the pump's configuration.
And that's where this master specifier, James Riggins, comes into the picture. His role is to prevent that mismatch.
Exactly. Think of Riggins as the ultimate technical risk mitigator for the pumping system. He operates way beyond just making a sale. His focus is on mastering the entire application context.
Okay.
His expertise is geared towards preventing that costly failure before the pump is even installed. It's about ensuring the configuration is perfect for the job it needs to do long term. That lifecycle guarantee posture we mentioned.
Let's get specific about the complexity he's dealing with. The notes mention something like over 110 different permutations for this pump. That sounds like a lot for just a pump. Why so complex?
It sounds like a lot, but it's because getting it right depends on hitting the sweet spot where fluid dynamics, material science, and the specific duty cycle all converge perfectly. Failure in any one of those areas compromises the whole system. Riggins is basically managing risk across 3 main technical domains.
Okay, what are they?
First is elastomer chemistry. This is all about the hose material itself.
Right, the only part touching the fluid.
Exactly. That hose needs to survive contact with whatever fluid it's pumping, potentially for years. So Riggins has to select the right specialized elastomer. Maybe it's a high-grade natural rubber if the main challenge is abrasion. Maybe it's EPDM for certain acids or caustics. Maybe it needs to be a fluoropolymer like Viton for really aggressive solvents or chemicals.
And if you get that wrong?
Disaster. If someone mistakenly specs a standard Buna N hose, which is great for oils but uses it for concentrated sodium hypochlorite, That hose will chemically degrade and fail in months, maybe weeks, not years. All the mechanical advantages of the pump are lost due to a material science error. Costs the client a fortune in replacement hoses and downtime.
So getting the chemistry right is non-negotiable. What's the second area of risk he manages?
The second is establishing the optimized RPM window, the speed at which the pump runs.
Why is speed so critical beyond just getting the desired flow rate?
Because speed directly impacts the heat generated inside the hose, especially with thicker, more viscous fluids. It also affects the mechanical fatigue rate. Riggins needs to calculate the ideal RPM range that delivers the flow the process needs, while also ensuring that single roller compression doesn't build up excessive heat.
Ah, so running it too fast, even if it delivers the flow, could cook the hose from the inside out, essentially.
It absolutely can. If an operator insists on pushing the RPM too high for a very viscous fluid just to hit a certain flow number, they might be dramatically accelerating the material fatigue. They could cut that promised 30–60% hose life extension right in half, or worse.
So he's balancing the operational demand against the physical limits of the materials to guarantee that longevity.
Precisely. He's ensuring the physics works in your favor.
Okay. Chemistry, RPM. What's the third critical factor?
The third is fluid compatibility, but extending beyond just the hose. It includes the connection points, the hose barbs, the flange materials, how it interfaces with the plant piping.
Why are the connections so important?
Well, imagine Riggins specifies the perfect abrasion-resistant hose for a heavy mining slurry. But if the hose barbs, the fittings that connect the hose to the piping, are made of a standard plastic or a less resistant metal.
The slurry will just erode the fittings instead of the hose.
Exactly. The erosive slurry will wear away the barbed material, potentially causing leaks right at the connection point. A hazardous situation, and again, it makes the pump's internal superiority irrelevant because the system failed at the interface. So Riggins has to ensure every wetted part is compatible with the fluid and the operating conditions.
Wow. Okay. So navigating those 110 plus permutations, it's not just picking options off a list, it's deep engineering knowledge applied to a specific context.
It's applied science. Elastomer chemistry, fluid mechanics, tribology, it all comes together in that specification. It's about replacing guesswork with engineering certainty.
And by doing that, he's essentially removing the single biggest source of variability or failure in installing high-tech equipment, human error, in the specification process.
That's a great way to put it. Specification error is eliminated.
So if Riggins gets it right, if the specification is perfect, what are the additional measurable benefits? Beyond the savings already inherent in the pump's design, what does his expertise deliver financially?
His contribution shows up clearly in plant availability and overall efficiency metrics. Getting that integration and sizing spot on typically increases the annual availability of critical process loops by 1 to 3%.
1 to 3% more uptime on a critical loop. Let's connect that back. If downtime costs $103,000 an hour, that 1% is, well, it's potentially hundreds of thousands, maybe millions saved per year just because the process was running when it otherwise might have failed due to a bad spec.
Exactly. It's pure profit protection delivered through expert application engineering. And there's more.
Okay.
He also adds another layer of OPEX reduction, separate from the pump's basic maintenance savings. By ensuring the pump runs at the lowest possible RPM for the required flow, and by optimizing component selection to minimize internal friction and stress, his work contributes an additional $1,000 to $3,000 per pump per year in operational savings.
Through even lower wear and potentially lower energy use due to optimization.
Precisely. Minimize stress equals maximize component life and efficiency.
And what about chemical costs? You mentioned the pump's precision helps. Does Riggins' work enhance that?
Definitely. Especially in processes using expensive chemicals where precise dosing is crucial. By optimizing the pump setup, calibrating the flow correctly, and leveraging the SoloTech's stable linear flow, Riggins helps plants achieve much tighter metering control.
Meaning less waste?
Meaning less waste. We often see chemical savings in the range of 2 to 5%. That comes from eliminating overdosing and ensuring accurate mixing ratios, preventing the waste of costly reagents.
Okay, so the complete picture emerges. You've got the Graco SoloTech pump as the core technology.
The superior hardware, sealless, single roller compression, built for longevity and leak-free performance.
And then you have James Riggins, the master specifier.
The crucial human element. He's the one who translates that hardware potential into guaranteed results in a specific plant environment. He navigates the chemistry, the RPMs, the compatibility, all that complexity.
Eliminating the specification risk.
Exactly. Ensuring that the engineering brilliance of the pump actually delivers the maximum ROI and reliability on the plant floor. It's the synergy between the two.
This whole deep dive, it really brings us to a fundamental choice, doesn't it? For anyone managing an industrial operation, it's not just about picking a pump model.
No, it's much bigger. It's a choice between two fundamentally different operational philosophies.
I blame that.
On one hand, you have the philosophy of, let's call it costly, cyclical repair. This is where you implicitly accept that a huge chunk of your budget, maybe that 35 to 50% we talked about, is just going to be consumed by managing inevitable failures. Fixing leaks, replacing seals, dealing with downtime as a cost of doing business.
The status quo for many, perhaps.
Perhaps. Or you choose the other path, the philosophy of proactive engineered reliability. This is where you invest in superior hardware designed to eliminate failure points, and you ensure its performance is guaranteed through expert integration and specification.
So investing in the SoloTech pump itself removes the inherent mechanical weaknesses.
Right? The seals, the valves, they're gone.
And leveraging the expertise of someone like James Riggins removes the risk of human error in applying that technology.
Correct. You eliminate the specification risk.
And the outcome is minimized downtime, maximized asset life, better stewardship of resources, and ultimately freeing up budget.
It boils down to this. Reliability isn't just luck. It's a function of smart design and correct deployment. You buy inherent stability with the sealless single roller pump. You guarantee that stability translates to uptime with expert specification.
So for our listeners, if you're looking at your plant's numbers and you see that maintenance budget creeping up towards that 35, 40, maybe even 50% mark, if you're constantly chasing repairs, cleaning spills, replacing the same components over and over, here's the final thought we want to leave you with. Take a hard look at your existing equipment. What hidden, maybe unnecessary complexity within those systems is actively consuming resources that could be driving innovation, expanding capacity, funding real growth.
Because that's the ultimate prize, isn't it? Choosing maximum reliability isn't just about saving money on repairs. It's about choosing operational freedom. It's about financial stewardship.
When you make that decision, when you invest in guaranteed uptime, you're essentially buying back time, buying back budget. You're shifting your team's focus away from the treadmill of repair.
And towards the profitable pursuit of progress, making things better, not just keeping them from breaking.
It really is time to choose uptime. That was the deep dive.